Welcome back. This is the first video of week 10 in inverse methods in heat transfer. What I wish to do in this video is to give you a brief introduction to week 10, but also a few additional topics are there. Specifically, we'll be looking at the XOR gate once again. We finished with the XOR gate in the last week, but I'll sort of naturally lead you to this sort of structure for neural networks that you can see here, which is one input, a few hidden layers, and an output layer. This layer is called the MLP, or the multi-layer perceptron. MLP stands for multi-layer perceptron. In short, it basically is a whole bunch of neurons connected in lines, and all these connections are full, and such a connection is also called a fully connected layer. So there are a bunch of fully connected layers between the input and the hidden layer. There are every neuron in one of the layers is connected to every other layer, neuron in the next layer, and so on and so forth. So this fully connected MLP is what we'll be coming to sort of naturally within this video. The main purpose of connecting things this way is we are able to use what is known as the universal approximation theorem, which I had briefly alluded to a couple of weeks ago. The basic idea behind the universal approximation theorem is that given sufficient number of neurons, if we are given sufficient number of neurons, an artificial neural network of the MLP type can approximate any function to a given amount of accuracy. So if I give a certain amount of accuracy, you can actually find out a sufficient number of weights which will approximate this function. Now, why does this come about? I'll briefly talk about that in this video. But the primary purpose of the week is to actually give you a full introduction to this structure called MLPs, tell you how forward propagation happens through this, and also how to solve solve for these weights through gradient descent, basically in effect solving an inverse problem. The next week after this one, we will look at how to use MLPs for various problems of our interest. Now, all of this utilizes a neuron, a basic structure called neuron, which I kind of introduced you to in the last week. The idea is very simple. When you have any of these coming in, you have a whole bunch of weights which come in here. So you could have W1, W2, W3. You sum those up and you run them through a nonlinearity. This is the fundamental idea behind a neuron. So the notations we will use are A is the output of a neuron. You can see here, A hat is the output of the neuron. From the previous layer, you could have A's coming in. For example, A from here would be input here, and A from here would be input to the next layer. Okay, so anyway, we'll come to this notation once more later on this week. But one thing I would like you to remember is the same thing that we did in logistic regression. You first have a linear combination and then you pass it through a nonlinearity. So this nonlinear function is called an activation function. And this function is simply a linear combination of the things that were coming in. Remember that for a neuron, multiple inputs come in, but only one thing leaves out. Okay, so we will discuss this in further as we go through this week. Recall also that we have been using gradient descent throughout. And one of the main purposes of this week is to do these two things in a little bit more detail. The forward propagation, which requires you to calculate the output of a neuron, and the back calculation, which requires you to calculate the gradient. Why we require the gradient, of course, is to update the weight within the neural network or any basic model that we have. Remember, we are doing data-based models. So these data-based models have various weights and they are updated using gradient descent, which requires you to find out grad of J with respect to the W. Last week, we also saw some variants of this gradient descent, the batch gradient descent, which uses all the data together, mini batch, which uses portions of data, and SGD or stochastic gradient descent, which uses each data individually. Now, before we step into this week, it is useful to see what we learned last week The reason for this is I will now put several things that we looked at in last week in one single framework. So the important thing to remember is that there are multiple models within machine learning, especially when you look at supervised learning. That is wherever we provide labels. All of these work in the same way. Now, it's useful to remember why these work in the same way. Remember, given some input data X and some guess for some unknown parameters W, so W are the parameters and X, of course, is the input. You run it through some model. Now, some various choices of the model I'm going to show you. One specific model is the neural network, but we had a linear model, we had a logistic model, we had sort of a multi-class model, etc. Any of these things can be just thought of as some model. When after this class, you look at other machine learning algorithms, it's useful to think of all of them within the simple framework. So you run it through a model. Once you run through the model, you get a prediction. Okay, so this prediction. Now, of course, you have your data, so you have the actual truth. And you have your prediction. So between the two, there is a gap. So these steps have specific names. This step is known as the forward step. So you move forward and actually calculate what your prediction is, or you can think of this as sometimes called the inference step. The next step is called the comparison step. So you made a prediction, there was some truth, compare the two, let's call it the comparison step. And the final step is the optimization step, or what we call as the backprop step. Some people call it the gradient descent step, okay? But let's call this the backprop step. Essentially what you require is, I am kind of abusing notation because backprop specifically applies here in calculating these gradients, okay? So this is really speaking backprop, but I'm going to sort of talk casually, and some people do that and say that the weight is updated using backprop, basically meaning calculating the gradient. So we have these three steps in every single model that you can think of, whether it's a simple model or a complex model. Okay. Now, what we want to do is to look at all the models we have looked at so far in this course in the same light. Okay, some of the models which we have used so far without using any hidden layers, let's call them single layer models. So a single layer model will function like this. There will be an input, there will be an output, and there will be no intervening hidden calculation going on. So the simplest model we looked at of this form is the linear regression step. What was the model? The model was here. Y hat is W transpose X. Okay. So this X can actually be a matrix, as I have shown later. For example, your X could have X1 and X2. In that case, if you have W is, let's say, W0, W1, W2, and X is, let's say, X0, which is just one, X1 and X2. We have seen this a few times. So this gives you W transpose X is W0 times 1 plus W1 times X1 plus W2 times X2. So that's what is written here in the linear model. I have written this as the mathematical expression. Okay, so what's written up here, if you are not able to see it clearly, is the mathematical or the analytical or the algebraic model. Okay, so for example, the linear regression model or the linear model is simply W0 plus W1 X1 plus W2 X2. These X1 and X2 are called features or attributes, and I'll come back to this point later on in this video also. When we represent the same thing diagrammatically, you have 1, X1, X2, you sum the three together, multiplied by W0, W1, W2, and you get y hat. We saw this the last time. Okay. Now, when it comes to the data representation, as I told you in the previous videos, it's a good idea typically to scale these input data. That is, you have x1 and x2. Suppose you have temperature going from 10 to 150. It's generally a good idea for gradient descent to work to rescale it so that you write it in terms of theta, some normalized coordinates, so that it scales between 0 and 1. I didn't emphasize this too much, but it's a good idea. In neural networks, there is an equivalent which is called the batch norm. We are going to ignore that, as this course is a fairly elementary sort of portion of our entire course. So I'm going to skip this, but just for your knowledge, in neural networks, this is known as the batch norm. Okay, the generalization of this is known as the batch norm. The final thing is the cost function. The cost function is J is simply a least square cost function. This is what we use typically for linear regression. So this is called the least square cost. Okay. What happened when we looked at the logistic function? So the logistic function is generally used for classification and typically binary classification. And there we had y hat equal to some g of z, where z is again w transpose x, same as before. And but we used the sigmoid as a nonlinearity. So we represented it this way. You sum these up and then run them through this sigmoid, and then you get an output. You see that there is still nothing in between these two. Nonetheless, in this case, you have two things going on. You have a linear function activation, and then you have a nonlinear activation through the sigmoid function. Now, what was the data representation? Y was either 0 or 1. It was either, basically, it was a scalar and it was binary. And the output y hat was between 0 and 1 again, but it was not discrete. It was not binary. It was a real number, and it represented the probability. Now, cost function, if you remember, was the BCE, or the binary cross entropy loss function, minus y ln y hat minus 1 minus y ln 1 minus y hat. We did this last week. The final example we did was for multi-class classification. Notice once again, Z is W transpose X remains the same. It's still the linear activation. And what you have at the end, of course, is a softmax. So I had given you reasons for why we use softmax in order to normalize properly in the last week. What does it look like? Instead of having only one output, you could have multiple outputs. Let's say it's a 3-class classification problem. Once again, every neuron in the input is connected to every other neuron in the output, and you get a y hat, which is a vector. The representation of y was a 1-hot vector, and y hat basically represented the probability that it belongs to class 1, class 2, class 3, etc. So you would have these 3 sum up to 1. And we had the categorical cross entropy loss function here, which was minus sigma of y ln y hat. I had also talked about the connection between the two. Now, what is the use of reviewing this? The reason is that we are going to try to integrate all these, and as well as the lessons that we learned while finding out the gradients for this, into this one single picture. So the purpose of this week is to sort of the grand unification of all the methods that we have seen so far into one single thing, which is a neural network. So the topics that we are going to cover, this video, the current video that we have after this short introduction, I'm going to cover the motivation for deeper networks via XOR. I briefly referred to it in the last video also, but I'm going to dig a little bit deeper in this video. Next, we will look at the forward pass. That is, how do you start from the input and go to the output for a neural network. Then we will do remember the comparison step is trivial, but the back propagation step is non-trivial. Typically, this takes a lot of time for students to understand. So I am split it into 3 different types of networks. One is the kind of networks that we just did, which are lots of neurons, but input and output are immediately connected. So this is a shallow network. So that's what we will do first. We'll find out how to find gradients for W, for all the W in such a situation. The next one is what I call a scalar chain. It is a deep network, but there is no width at all. So there is only a single neuron in every layer, and we just go through that deep network, and we will try to do back prop there. And after we are done with that, we will come to this final case, which is a normal multi-layer perceptron. Of course, I'll do a sort of simpler example here also, but by the end of this, you should be clearly able to understand how it is that gradients are calculated in a general neural network. Finally, I have only talked about sigmoid activation function. We will talk about various other activation functions, and in the context of backprop, we will talk about why these various activation functions are required. So let's start with the first topic for this week, which is the XOR problem. So remember that logistic regression works only for linearly separable data. I had talked about this the last week. So I had sort of made up some classification examples. So these, for example, these three are elementary gates. This, for example, is what's known as the OR gate. I had discussed this the last time. The OR gate, remember, is a simple case where you are only trying to classify 4 points. Really, there's no generalization here, which is OR, you remember, 0, 0 gives you 0, 0, 1 gives you 1. If either of these are active, that's why it's called the OR gate, you get 1. So I have denoted here green as 1 and red as 0. So this is a simple OR gate example. Now, when I say OR gate, all of us can intuitively draw a classification line. Okay, so this classification line we can draw. Let me draw it in dotted lines so that it's a little bit big. So if you look at this line, let's say this passes right in the midpoint, half, 0, and 0, half. So this would then be the line 2x1 plus 2x2 equal to 1. Okay. You can simply check this calculation very simply. If I set x2 to 0, then x1 is half. If I set x1 to 0, then x2 is half. So this is the line which passes right in the middle. And this is the classification line. Now, remember, we had also seen in the last week that the line, which is the classification line, is the line where z equal to 0. Okay. So this z equal to 0 line is the classification line. So here, for example, you can say z equal to 2x1 plus 2x2 minus 1, which in this structure here, if you remember, z was also equal to w0 plus w1x1 plus w2x2. So by our interpretation, w0 is minus 1, w1 and w2 are equal to 2. So that is because the coefficient of x1 is 2, coefficient of x2 is 2, and the constant term when it comes on the left-hand side is minus 1. So there is a one-to-one correspondence between these three: the algebraic expression for z, the picture here, and the classification line. Now, I had talked a little bit about this last week also, but I will say again that when you have a straight line, it has the equation w0 plus w1x1 plus w2x2 equal to 0. And z physically represents the linear activation here. Z physically represents this classification line. Now, if I similarly draw the classification line here, okay, so now I want to separate these three green points from the red point. This, of course, if you can see it, is the AND gate. I think I have drawn it in the wrong color. Let me just change the color here. So these three are off. Okay, 0, 1, 1, 0, 0, 0 are off, and this one thing is on. So this is the AND gate. Okay, so the AND gate is going to look like this. Now, just by inspection, you can sort of write the equation for the AND gate. You can see that this will be around 3 by 2 and this will be 3 by 2. So you could have something like 3x1 plus 3x2. I had also done this algebraically in the last week. So minus, let's say, 2 equal to 0. This would be the equation for the AND gate, so that when x1 equal to 0, x2 equal to 3 by 2, so on and so forth. Okay. So this would be the AND gate. So that means that you can replicate the AND gate by another network whose weights are -2, 3, and 3. So just like the OR gate can be replicated by a network with W0 equal to -1 and W1 and W2 equal to 2, AND gate can be replicated with W0 equal to -2 and W1 equal to, let me write that down instead of just saying it. So this could be W1, this could be W2, and this could be W0. Finally, this one is an example of a flip gate. This is the OR gate, sorry, this is the NOR gate. You will see it is exactly the opposite, or it's not of OR gate. So NOR gate. Now it seems to have the same classification line as the OR gate, except we are going to write the other way around and flip directions. So here Z is basically -2x1 -2x2 plus 1. So the weights are exactly flipped. So as I had told you, this one will be 1 on this side whenever this distance is positive, and it will be 0 here. This one is exactly the opposite. It will be 1 here and 0 there. And as I had also indicated last week, really speaking, the data points we are looking at in realistic scenario are more like this. Okay, so you'll have lots of data points here and some other data points here. So you will have a lot of red points here, red points here, red points here, and green points here. Obviously, it's somewhat as if you are just selecting 4 data points. So why all this exercise? The reason is each NOR, OR, NOR, and AND can be simulated using logistic regression. As I told you, this allows us, allowing a simulation of elementary gates allows us to simulate more complex logic. This was the basic historic idea why people looked at this. So if we look at the XOR gate, so the XOR gate is like this. If you have both the same, whether it's 0, 0 or 1 and 1, you're going to get 0. So this and this are going to be 0. If the two are different, 0 and 1 gives you 1, 1 and 0 gives you 1. So for example, both are different, you're getting this. Now the problem is this cannot be linearly separated, as I discussed in detail last week. You can, however, separate it using some curve of this sort. This is a non-linearly separable. Okay, so both are true. It is not linearly separable as well as it is separable but non-linearly. Okay, so you have to make a non-linear surface somewhere around it to make it separable. Okay, so since that is the case, I'll tell you a couple of expressions that will achieve this. So for example, if it were linearly separable, then you will be able to get some expression which will look like W1x1 plus W2x2 plus W0, which would be a line which will separate it, which we know is not possible. But now, if I look at another expression, x1 square plus x2 square minus 2x1 x2. Okay, so if you look at an expression of this sort, this of course is x1 minus x2 the whole square. You will see x1 minus x2 the whole square is 0, x1 minus x2 the whole square is 0, and x1 minus x2 the whole square is 1 here. Okay, so this actually works. But the price you pay here is you have now introduced new quantities. We only knew x1 and x2. Now you have introduced x1 square, x2 square, and also a cross term x1, x2. In fact, not just x1 square plus x2 square minus 2x1, x2, even x1 plus x2 minus 2 and x1, x2 works, because when x1 is just 0 or 1, then x1 square and x1 and x1 square and x2 and x2 square are the same. So this one works as well. Now suppose I were to represent this as a network. How would I do it? The way to do it is as follows. You take an input, we have done this before, you take an input x1, you take an input x2, you also take a third input x1, x2. Now it should seem, you will think, well, why should I need this? I have already given x1 and x2. The reason is these are only linear combinations. So this is never going to arise unless you add it explicitly. So typically, what we say is x1 and x2 are attributes, that is the original properties we were given as inputs, but x1, x2 and x1, x2 are features. Features meaning you put these together. So for example, you want to say somebody's face is beautiful, you might say both the eyes, they have good features. That's because it's not just the original single eye, left eye, right eye you're looking at the combination of the two, or the combination of all the features put together. So these combinations that occur, these are the features. Okay, so you can simply do linear regression for this data set. But the catch is, just like the quadratic and the cubic regressions that we did earlier, this linear regression works only if you give x1, x2 explicitly. Okay. But the key question is this, how are you going to know magically that you need x1, x2? So rather than saying how do we get x1, x2, which is just a simple calculation, how do we get to know that it was x1, x2? Now here the data I took was simple. I just took 0, 1, 1, 0. What if, it was a numerical data and I needed x1 square x2 or x1 cube x2 or a whole lot of other possibilities? So what happens is, in general, it's not possible to discover these or keep on giving a list of all possible combinations systematically in higher dimensions. Higher dimensions means here we are just dealing with two variables. But if I deal with multiple variables, which I typically do in machine learning, now high number of variables, high amount of data. This is the general catch behind machine learning. This is generally not possible. And that's what is known as the curse of dimensionality. That is, you cannot arbitrarily provide these features intelligently or systematically in higher dimensions. This is where we have our deep learning algorithms. So the idea is what is known as representation learning, or in our case, let's call it feature learning. How do I find these features out automatically? So for that, what we need are deeper networks. That is, we currently had no depth at all, no hidden layer. And the catch is, if you want to achieve things without hidden layers, you have to pay the price by adding a large number of arbitrary features here. Instead of that, if somehow you put a middle layer, okay, you add a middle layer here and you do some unknown computations, or you do some computations with unknown meanings, then you result in deeper networks. So I want to show you how that happens in XOR via a deeper network. So as I told you, the XOR network can be written in terms of simpler logic gates also. For example, the XOR truth table that I showed you, which was 0, 0 and 1, 1 give us 0, and 0, 1 and 1, 0 give you 1. It can be written as this combination. You had x1 and x2, apply a NOR. Then for the same x1 and x2, apply an AND. Then put a NOR of the output of this two, and that will give you XOR. So another way of writing it is, let's say, NOR of x1, x2 is A1, AND of x1, x2 is A2. Then you do NOR of A1, comma A2, and that will give you XOR. So just to show you that this is true, remember I had written NOR of x1, x2, NOR of, AND of x1, x2, and NOR of A1, A2. Okay, so this is how these quantities were calculated. So just as an example, if you have X1, X2, if I do NOR, OR gives me 0. So NOR is just not of OR. So that gives me 1. Similarly, if you do AND, I get 0. Now I take 1 and 0 and I do a NOR, I get Y, which is 0. So you can repeat this exercise and test it out. And you indeed get the XOR outputs. So for example, 0, 0 gives you 0, 1, 0 gives you 1, 0, 1 gives you 1, and 1, 1 gives you 0. Notice how it achieved it. Some of these outputs were sort of stringed together. You got the same output here. You got somewhat flipped outputs here. But the catch here is these two. These two are intermediate calculations. These intermediate calculations made it possible to calculate Y without ever, notice we never invoked x1 square or x2 square or x1, x2. You only invoked the linear features, x1 and x2, but you did some intermediate calculation, and that's how Y suddenly magically came into being. Now we can represent this as a network. How so? So for example, remember that we had all these weights from before. So for example, this was x1, this is x2, and this one is supposed to be NOR of x1, x2. So suppose I say that I first do a NOR, just like I did before. So all we do is use the weights that we already knew. The NOR weights were given here, right up here. So the NOR weights were W0 is 1, W1 is -2, and W2 is -2. So you can just write those weights here. W0 is 1, W1 is -2, and W2 is -2. Now it turns out that let me do this in a short while. So similarly, the second one is AND. The AND gate, if you remember, was 3, 3, -2. So this one would be -2. This one is 3, and this one is 3. So what comes out as output here is what we call A1. This one is A2. And this one is, as usual, the bias unit. Now, this gate is again the NOR gate. So it has the same weights as before. So the same weights as before happen to be 1, -2, -2. So you combine this network together with the hidden outputs being A1 and A2. In this case, we can interpret it. And the final output then is going to be Y hat is XOR of x1, x2. Now, I want to point out that all these, to assume this, of course, we assume that there was sigmoid here, sigmoid here, sigmoid here. As it turns out, this won't be exactly XOR because there is a sigmoid which will give you an input between 0 and 1. At the end, you have to do some thresholding. This I showed here. Typically, when we say that the output is an OR output, we want 0 or 1. Obviously, the output is not going to be that. It's going to be greater than 0.5 or less than 0.5. Let's say the output comes as 0.6. Then if you want the output, you have to put a step function here. So you have to put some step function here. And this is the thresholded output, which says that greater than 0.5 goes to 1 and less than 0.5 goes to 0. However, when we take the gradients, they are taken from the non-thresholded output, the direct output of Y hat, because after thresholding, you can't really differentiate. You can only differentiate the sigmoid. So you calculate the sigmoid, you'll get a J using our binary cross entropy, and then you do a back prop or you do a gradient from there and collect W0, W1, and W2. Okay. So similarly, when you actually run this in practice, you have to be careful about whether you have, you will not actually achieve this. This is sort of a toy example, but the primary purpose is to motivate that a deep network actually arises naturally if you only want to use these linear terms, provided you are willing to expend these intermediate calculations. So what happens here through this entire process is this allows us to create approximations systematically. Remember, our entire purpose of using a network is to create an approximate model connecting the input to the output. Okay, so this is our entire purpose. Now, if I have 4 inputs, I want to create x1 square, x2 square, x3 square, x4 square, x5 square, x1, x2, x2, x3, etc., etc. That just becomes humongously expensive, as well as we really don't know which all terms to take. Okay, should I take cube? Should I take power 4? How many terms should I take? That is why it is easy. Like when we feel that the approximation is not good enough, we simply add more layers or we add more neurons. I'll come to somewhat of the subtle distinction between these two in the next couple of videos. But nonetheless, we will basically achieve our purposes rather than touching the input, which we keep as it is. We start adding stuff in the middle. And as it turns out, that's good enough. In fact, we have the universal approximation theorem, which says that if you just give me one layer, okay, just give me one intermediate calculation layer, as mentioned here, even with one single hidden layer, you can approximate any function to any given amount of accuracy, provided you give me sufficient number of neurons. So that is it for this video. In the next video, we will start seeing how to actually move through this network from beginning to end. Thank you. I will see you in the next video.